Now we talked about safety. How do we get now safety into the system? Because if there any component, as said, can break. So at the end, you need to observe in a parallel way with what happens within the systems. So that's really the important part in safety, that you have some redundant look on your properties. It depends on the security level, how much you need, but at the end, that's the idea of safety. Do it twice. So you have an observer checking if everything is okay, and then if something happens, you have error handling, bringing the car or the vehicle into a safe state. So if we detect there's some problem with security, and you don't want the car to accelerate for itself, you bring the car to a safe state. So that's more or less how safety is brought into systems. And the way you bring in the services and what's really the error handling, this can be a quite intelligent functionality, or this can be a really quick and efficient or fast functionality. It will be some quick and fast functionalities. So that's more or less the smartness of the car you have, how intelligent the functions are. Okay, then I go a bit faster through this. We have a lot of third-party requirements. So you need tools for loading and testing. You need flash programming, so you have to bring new software on the device. You have development, testing things. You have rapid prototyping. That's a quite interesting way to test concepts you have in mind. Measuring calibration, because you want to define the behavior of the car in a late stage, that you more or less just develop the system for itself, and then after you have more or less finished the product, you want to fine-tune. So you want to say, okay, how's the real behavior? And that's where we have a lot of test drivers at BMW going to ice, to desert, to different conditions on different tracks, on racetrack, on normal street, and so on. They drive and drive and drive, and they fine-tune the parameters of the car, and that the behavior afterwards is that you have a real BMW, and the feeling of the BMW is experience everybody can have, so that if you switch the cars, that you even feel, okay, it's a BMW. So that's quite important for us, that you have the possibility to fine-tune all those small behavior things and attributes. Yeah, and off-board diagnostics, of course, if you go to the service, they need to read out information. Okay, so next step, it's getting deeper and deeper. At the end, you have software components, so you know how the software interacts with each other. Now you have to map and bring this software to hardware, and that's exactly done here. You think about connections which are direct linked, which go through buses, and you more or less partition on different things like ECU load, on timing issues between the software components about the partitioning. Yeah, then you can do out of the control architecture we have discussed earlier. You more or less do the same on the software components. So you know the interfaces and the communication in between. Oh. And the second thing is you have to consider which states you have, because often you have sort of use cases you use within the car. So probably think about if you come to a car, you probably press on the remote to open the car. So that's more or less you don't drive, it's coming to the car, pre-drive. Then you sit within the car, you start the engine, so you have a sort of starting event. Then the next thing is you drive the car. Then you have probably some after driving, like you check some emails within the infotainment system or whatever. So you have different states you want to describe. The same you have for technical systems within the car. So you can you have some possibilities for windows. You can move up windows. You can move down windows. So that's more or less the idea. You just define the states which system can have, and out of this you describe the behavior, and you think about the reactions and actions need to be taken within this state. It's a quite important tool for us within function development. Yeah, and then the second view on the things is the data flow. And here we come to the world MATLAB Simulink. You probably know, most of you know, where we describe the behavior not in the states, so more abstract description, but we really define the data flow. So from component to component, which information is transferred, and this is exactly the point how we model. Now we come to the model-based development. So we did a lot of pre-work. We have really some idea how we define the things. We know the requirements, and now we model the information which is flowing from software component to software component. And within those blocks, we have, for example, the yellow one is a bit shown. We have some state machine where we describe the states. And so on. So that's the point where we bring all together in some model-based functionality. Now we develop. Now the interesting thing is how can we organize all this work? Because within the BMW i3 we had hundreds of developers all working together on this project. So you have the problem if everybody works on his own. And one day someone finishes his functionality, but probably he needs the input of some other developer, and you have to control this, or you have to define the time frame you're working on, and that's exactly what we're talking now. So more or less you can have a classical model where you define some release steps, major release, and you put some minor release steps within. That's quite popular within industry to work in this waterfall model. So more or less you have a major release, you define what's the result we want to have at the end, but within you define smaller steps where you want to release. But you have one big problem at this, because we have quite fast development cycles. You probably have a quite fast release cycle, so you have in parallel more than one software path. So you work on one, and you already started for the next path. So every of those bullet points is more or less a release of functionality, and so you have. Sometimes if you find a bug or you have a parallel software things, you need to release it more than once, or if you work in a construction kit, for example, we use a lot of functionality within the i3 and the i8 cars. It's the same function, but if you find some software bug within one car, you have to transfer to the second, but probably you have no nearby release, so you have to do it in a sort of split way, and that's quite hard to handle at the end. And because at the end you have all the functionality left, so you can really test the system only at the end in complete way. You have really a late detection of errors. The different approach is Scrum, so it's agile methods, where you define fixed development cycles, really small, short development cycles, and you you release every 2 weeks or every 3 weeks or every 4 weeks, what you define. You release every time a software. And important on agile methods is that you be in time, and so the idea is that the timing is more important than the contents in first place, and so the advantage is you get more early release candidate, and you can detect errors in a more frequent way, and you have the possibility to include some construction kit issues that you just say, I release for every car all 2 weeks new software, and I can test it. So it's more or less a different approach about how organization is working, so agile. Good. Now, more or less, we have the functionality, and now Peter is giving you some impression about how the software part is now taken.
Thank you, Patrick. So, yeah, Patrick told you something about how to develop the function, getting from requirement to, let's say, a MATLAB model or a state chart, and then generating a software component, and now what to do with that software component. Yeah, of course, we have to bring it on some control unit. This process we call integration. And the function itself, the MATLAB model or the software component itself, will not run alone. So we need some operating system. And the idea was to have a standardized operating system. Going 10 years back in the automotive software history, there used to be no standard except every car manufacturer had his own operating system on each control unit. But the question is, what is the need of it to have our own operating system? You could compare it to Apple iOS or Android. The question is, do they make their money with that? And the car manufacturer decided that they don't want to make money with the operating system, so there is no need to have a proprietary solution. And so all car manufacturers sat together and made a common standard, which is called AUTOSAR, Automotive Open Software Architecture. Yeah, and this basic software had several goals. So first of all was the goal that we don't want to write the software again and again for each car. We want to reuse it. Question is clear. First of all, we identified all the problems. The first time we made it, we fixed it, and then why should we do the problems or the failures again, or redevelop the software? So let's reuse it. The second is, if you have a standard like, let's say, Linux, everybody knows Linux. A lot of you may have done some programming already on a Linux machine. Some of you may have programmed an app or something like that. So you know these standards. And the idea was also to have a standard for the automotive industry with a result of a common understanding between the supplier and the OEM, and also the possibility to get educated developers from universities. So there are automotive or AUTOSAR courses at the university, for example, and the developers come already quite well educated from the university. And moreover, if you as a supplier, if you had a project, let's say with BMW, and then switch to a project, a software project with, let's call it Tata or whatever, then if both use automotive standard, then the operating system is the same, and the developer knows already what to do. Another goal was to improve the quality despite increasing complexity and innovations. Looking again 10 years back, most of the problems car had at the customer were software problems, and a lot of cars, so they had problems, and the idea was to improve by having an operating system standardized, and this is one thing, and the other is, of course, as Markus already mentioned, that more than 90% of the innovations are from software and electronics, and in average, more than 30% of value added inside the car is also software or electronics. So if you look at a car and say it's let's say it's $20,000 cost, so then about $7,000 are spent there in this car for software and electronics in average. Huge number. So therefore the idea was to have this automotive standard, and the question was how can it be achieved by using a standard? And there are three main topics. The first of all is the methodology. So if you see, let's say at C, at the programming language C, well, you can use C in any way you want to use it, yeah. So it makes it safer, nevertheless, to use C in a specific way. Like you say, I want to have a lot of modules or capsulated modules. So this is the methodology, yeah, the way you use it. And you could also have, instead of using this methodology of modular programming, you could also have one .c file. This would work very well, but it would not help in managing all the functionality in this project. So the methodology, therefore, was to say with AUTOSAR one should be able to develop from top to bottom or top down approach. So looking at the system, going to the subdomains and so on, and then go onto the control unit. And this is what we call top-down approach. Yeah? And AUTOSAR provides a uniform description format in XML for configuration of the basic software. So this is one of the main topics, how to achieve the mentioned goals of the standard. Another issue is the architecture. So the software architecture, to be precise. The idea was to have the application software, to have the reuse I mentioned, is there needs to be some mechanism which allows the software to be developed hardware independently. So the idea is having specific layers at the having layers at the architecture. So mainly 3 layers. In detail there are a little bit more layers, but there are 3 layers. So we have the application layer. We have the so-called runtime environment, which is responsible for communicating between the application parts and the operating system. And we have the operating system or the so-called basic software. So, so this is how it was done, to have the architecture independent or provide an independent architecture for application. And the last issue is standardized application interfaces. So with this you can say we always have velocity as velocity or force as force, or moment as moment, but not as float or as 16-bit float or 32 float. Yeah, so standardize the interface between the applications. By this, you can, of course, reuse your application software, yeah, because you have always the same interfaces. You talk always about velocity. So how is it done in reality? So you go top down. Patrick developed all the software components which are necessary to fulfill the application of the system. And in the function development, one is not interested in via what bus the software components communicate with each other. It doesn't care. It doesn't even care whether the software components are on the same control unit or on different control units in the first step. So this is what we call the logical architecture. We're just interested in, we have those software components and they communicate with each other. And to realize this, AUTOSAR developed the concept of a virtual function bus, meaning this is the bus, which is not a physical bus, but a virtual bus, over which the functions communicate with each other. And this is the top-down or the system level. And in the next level, when you map your software components to specific control units, you get the derived communication and automatically get the runtime environment I mentioned, which is shown here in red. So this is responsible for the communication, and this is generated automatically out of the information which you see from the virtual function bus. So the virtual function bus knows which software component needs what data. This is specified in the logical architecture. And by the mapping of the software components to the control units, one knows which data have to be exchanged over the bus or only locally to the software component. And this mechanism is handled by the RTE, the runtime environment. Here is shown in detail. The virtual function bus knows the communication needs of each software component, and you have an interface to the runtime environment or to the virtual function bus. And if, let's say, you distribute the first two software components onto the same control unit, the virtual function bus realizes this and just generates the right communication mechanism for the RTE. And if you distribute them on different control units, then the RTE is generated that it passes the information to the bus driver, let's say CAN driver or similar FlexRay, whatever your bus system is. So the basic workflow is you have the system configuration, meaning all the software components needed in the system together with the communication between the software components. This is the system configuration description, and together with the set of control units, and you get the ECU configuration, the control unit configuration. Later on, you can generate, by mapping the software components to the ECU executable, and you get a component-related template for each software component, which means you get the function calls to the RTE. This is generated automatically to establish the communication. And this is the basic top-down workflow for AUTOSAR. So now let's have a little bit closer look onto the details of AUTOSAR. And as I promised you, AUTOSAR has a little bit more layers than only 3. What you can see here is on the bottom we see the microcontroller. And we have several layers onto it. The first layer is typically called the hardware abstraction layer. And then you have the for specific stacks, you have more abstraction layers and so on. And then you get the RTE. which abstracts from all the operating system details to the application. So idea is whatever you change below the RTE is not of importance to the application. And therefore you can reuse the application. So what we have seen in these pictures, we have several services, or stacks, so-called stacks, which is the this is one stack, this is the memory stack, the communication stack, and so on. And this is how AUTOSAR is built up. The system services does more or less things like scheduling. Yeah, so who is gets all the microcontroller resources. The device stack provides or manages the additional devices, for example, watchdog devices or things like that. And the storage stack abstracts between different types of memory. You can have flash memory, you can have EEPROM and things like that. And you can even have external flash or internal flash. And the memory stack provides a uniform interface to all those stacks so that the application does not have to take care about to which storage stack the data go. It has to be configured only in the runtime environment. Then the communication stack handles all the bus system, even the local SPI, for example, and also the CAN bus, FlexRay bus, and so on. And I/O stack, meaning if you have some AD changer or digital I/O, this is handled via this stack. And the last thing is the so-called complex device drivers or complex drivers, which are used to bypass all the other operating system services. If you need very fast software functionality, then you can use complex device drivers, for example, for combustion engines. They have timing requirements on a microsecond level. This is one use case. The other use case for complex device drivers, if you have old software, which is legacy code, meaning legacy code which is not AUTOSAR compliant, and you want to reuse these, then put them into a complex device driver and they can be used in an AUTOSAR environment. So that's on the AUTOSAR. Finally, summarizing, what we have seen is that our requirements for automotive software differ from a typical classical IT, more or less. So most important are safety and reliability. Looking at the brakes, yeah, we don't want to have a blue screen using the brake. We have performance issues. Yeah, one question, what do you guess, how long or how fast have ABS systems or brake blocking system? How fast does it have to be calculated? Yeah, very good. It's 7 microseconds is the cycle time of the ABS systems. So very good. Yeah, so we have real-time requirements. Yeah, so not like using databases or web services. There are hard real-time requirements. We also have legal issues, consumption and emissions, and moreover also some environmental, which is humidity and temperature. Yeah, from the function development, we have seen the process from requirement via architecture to the model and software, and finally you have to test the software. And as last point, we have seen AUTOSAR as standardized operating system, which helps to reuse the software and provides a methodology to handle the complexity by using a top-down approach from collection of software components down to a mapped control unit system of the technical architecture. So this was it from our side, from Patrick and my side. Are there any questions from your side?
I have a question for Mr. Schiele, and this is your Mr. Schiele.
No, it's Patrick.
Sorry, Mr. Hellwig. It was about the work organization. You talk about two models, the classic waterfall model and the Scrum model. And my question was, if you release the specification or the product every 4 weeks, how to make sure that you spend not too much time in meeting and spend enough time for your team in development? And the second question, how to make sure that your engineer will accept this quick release and this often release? Because maybe and third question, do you use also this model for hardware function or only for software? Because for hardware, if you have to change the layout, for example, then it can a release of the specification can have some huge changes in the layout, and then it will delay it for the project.
Okay, first I try to repeat your question that I understood correctly. The first question was, how do you manage that you don't take too much time on the specification side and you can start early to really develop? More or less, we have, first of all, we have defined product life cycle or development for the product life cycle, where we have defined time frames where we more work on the specification and later work on the development. So more or less that's out of experience. So we have defined life cycle where we really have milestones. Until this point we do the general specification, and then it's fixed, it's written down in documents, and then we have a sort of change management during development, that if any change or any problem happens, we more or less handle this by change management on the existing specification. So that's how we make sure that we have enough time for development. Second question was this your question, or?
Does the system also exist in hardware module, in hardware development?
If we use also agile methods in hardware,
yes.
Right now the development cycle for hardware is quite long, so makes not sense to do agile in an extreme way. So in agile methods you have a lot of tools you can use, but more or less to really have a 2-week loop or something like that makes no sense for hardware.
So it's more for software.
Yeah, it's really software based.
And perhaps a question for you, Mr. Schiele. You talk about the timing requirement for the calculation of some ECU. You say it's 7 microseconds for the brake checkup, but this is not for all modules. No? You have some function in milliseconds and some other.
Yeah, so this is more or less, let's say, we have functionality which calculates the sensor values in a microsecond level, and we have functionalities which run on 100 milliseconds cycle. Yeah, so there we have not only one cycle, but we have a kind of multitasking operating system which allows to have those multitasking parts, so with a 100 millisecond task and a 50 millisecond task and so on.
Thank you.
So any further questions? Okay, thank you very much then.
No, thank you.
Markus, you have some words on to wrap it up? ครับก็ wrap up นิดหนึ่งนะครับก็วันนี้เราคงมีโอกาสอันดีที่ได้มารับฟังนะครับก็อย่างที่เล่าให้ฟังตอนต้นนะครับอันนี้ก็เป็นเซมินาร์ครั้งแรกนะครับของสิ่งที่เราตั้งเป้าไว้ว่าจะเป็นเซมินาร์ซีรีส์นะครับ Smart Mobility Seminar Series นะครับที่เราเป็นความร่วมมือนะครับทางนั้นจุฬานะครับแล้วก็ทาง BMW แล้วก็ ThaiGerTec ซึ่งเป็น local partner ของเรานะครับก็แชร์นิดนึงใครที่ได้ไปสัมผัส i3 มาแล้วเนี่ยนะครับก็คือทางด้านณปัจจุบันเนี่ยก็คือบริษัท ThaiGerTec เนี่ยก็จะเป็นบริษัทที่ได้พัฒนาตัวซอฟต์แวร์แล้วก็ตัว embedded system ของ BMW i3 นะครับเพราะฉะนั้นเนี่ยผมก็เชื่อว่าณปัจจุบันเนี่ยต้องยอมรับแล้วว่าเทคโนโลยีที่อยู่ในระดับโลกเนี่ยแล้วก็คือได้มาเริ่มทำงานพัฒนากันที่เมืองไทยแล้วนะครับแล้วก็หวังว่าในโอกาสต่อไปเนี่ยเราจะได้มีโอกาสนะครับมาแชร์ในมุมอื่นๆอีกนะครับวันนี้คงเห็นภาพแล้วแหละว่าในเรื่อง Automotive Electronics เนี่ยเป็นเรื่องที่ค่อนข้างกว้างขวางนะครับแล้วก็จะมี aspect ต่างๆเยอะแยะนะครับจะเป็นทางด้าน safety ก็ตามเป็นทางด้านสิ่งแวดล้อมก็ตามนะครับหรือเป็นทางด้าน industrial development ต่างๆก็ตามนะครับเพราะฉะนั้นในซีรีส์ตรงนี้เนี่ยเราก็คงจะได้มีโอกาสสื่อสารกับทุกท่านที่มาร่วมวันนี้นะครับว่าอีเวนต์ครั้งหน้าเนี่ยเราจะโฟกัสไปที่เรื่องไหนยังไงได้บ้างนะครับ